So in this new section here, we make a few more comments on the nature of the parallel computing problem. So we remember here's Hadrian wall, this is the problem, and we chop it up, and then we see that each bricklayer is solving this sub-problem. And this is a point I made earlier. If I compare the full problem, which is to build this wall, with the parallel sub-problem, which is building this wall, you can see what's happened. The geometry has changed. Maybe this is a smaller size wall than this big wall. Also, the boundary conditions have changed. Previously, the boundary conditions was a flat edge here and a flat edge here. Now we have boundary conditions that you must talk to your neighboring mason and get these joining bricks to properly link up together. So then if we compare that with programming here, it says Hypercube, but we need to replace that by general cluster. So this particular slide was written in 1984, pretty old. So we have that the equivalent statement is this is the single program multiple data idea. Every node runs the software that's similar to the sequential code, such as being written in those days. It was usually written in Fortran. Even nowadays, several of these codes are written in Fortran. And we change the geometry in the boundary value sections. I gave you some illustrations earlier of how you could have pretty irregular problems. I did the airfoil where all the action was next to the wing, and we can get some load imbalance in Hadrian's wall by having specialized towers where maybe we have our archers sitting waiting to monitor that the barbarians on the other side don't do anything bad. And so we might have taller parts of the wall every now and then. So that's an example of, and then to get some load balanced bricklaying problem, when they try to make roughly equal numbers of bricks per mason, which means the mason doing this case here where the height is smaller would get a larger length than the mason responsible for these parts where the length is smaller. So we do equal work, not equal length. When we are doing the decomposition. I should also note the masons don't all work at the same level of energy, and they don't all lay bricks at the same rate. That actually makes the human problem a little harder than the computer problem, because typically in the computer problem, you usually go for cases where every node is identical. It's not always true. You can have heterogeneous clusters and have different nodes. But at least you know sort of precisely that this node is 3.2 times the performance of another node. With humans, it's not so easy to characterize performance of humans in a reliable fashion. So here's a inhomogeneous problem. Emperor Hadrian said he wanted his wall to be prettier, so he put some gargoyles on the wall, namely decorations. And we then still have the same partner. We're building a wall. We can build each section separately, but some of the sections are much more complicated than other sections. They have a completely different problem to be done, and we build gargoyles. And so it may not be obvious how long it takes to build a gargoyle compared to laying bricks. So that points out that we need quite subtle decomposition methods to make certain each of our masons does an equal amount of work. And this was, again, has analogies to the computer problem where we have, for inhomogeneous problems, we need very dynamic load balancing methods. And there's lots and lots of work in this area. We also note various forms of parallelism. The parallelism I've stressed is so-called global parallelism, where we break up the domain and assign different actual regions of the wall to different masons. And the parallelism is proportional to the size of the problem. And we have, typically for big data, we have lots of parallelism. And the unit of assigned to that parallelism is the mason or the computer node. We also have local parallelism. This is what's exploited by vector processors such as GPUs and things like that. And so if I'm a mason, I can use both hands simultaneously, and computers can either say do vector operations very fast, or even more simply, they can do addition at the same time as multiplication and so on. So you need to exploit all these forms of parallelism, and doing that optimally is sort of non-trivial. Well, most of our big data problems actually read from disk. And so what's the analogous to this here? Well, that is that we can actually supply our masons in parallel. So the analogy of the disk for Hadrian's Wall is this truck full of bricks, and that truck delivers in parallel bricks to one or more mason per truck, and we could have one disk each supporting 8 cores, say. So that would be multiple CPUs supplied by one disk, or else we could put lots of disks on our CPU and have a different ratio of disks to CPUs, and that's all has to be optimized, and will be different for different problems. And MapReduce is particularly effective in dealing with these disk-sensitive problems. So if we try to summarize what we've learned, we've pointed out that it's very important to have large problems, but that's okay because we're doing the big data. This is a big data course, so our problems are by definition large. So we expect to be able to use parallelism. We expect the edge effects to be relatively small, these overheads to not be so great. We do expect to see do expect to see inhomogeneities and complications due to that effect, but that's typically solved by various sort of statistical load balancing methods. We pointed out that we need to have a network that matches that needed by the application, and the slides are mainly focused on the classical scientific simulations where we needed local communication. If you go and look at those big data problems we discussed, most of those are not local. They tend to need so-called reduction operations or broadcast operations, where one node sends information to several other nodes. And as I said, although the simplest regular homogeneous problems are easiest, we know how to do irregular and inhomogeneous problems. We just need to do the correct decompositions and correct dynamic structure. We always use local and global parallelism, and we know how to do concurrent calculation at the same time as we're doing I/O. We buffer in the new data while we're reading it from the old buffer and so on. And when we have multiple nodes, we tend to use message passing because that is the cost-effective way to build large-scale parallel computers. So that's the end of this presentation on parallel computing. I apologize that the slides are very old. These basic ideas were first written down by me at least 30 years ago, but they're still roughly correct. And the only real change is in those days we were dominated by the local problems where we had each node talking to neighboring nodes, whereas in data analysis we tend to have different types of communication structure, which is that's supported by MapReduce and its iterative extensions, the so-called map collective model, where we have large-scale communication primitives. But still, the essential ideas are very similar. Thank you very much. This is Jeffrey Fox, winding off.